Live, and we should be live by now. So, welcome everybody to the 36th Data Science Leuven meetup already. As you can tell, we're still digital. So normally we do this at Stuk in Leuven, but due to Corona, you all know we're still on YouTube. I guess this will be the case for the remainder of the school year, right? So until June we'll be on YouTube, and then hopefully let's see how the situation evolves. But in September we can meet each other again at Stuk in Leuven and have some drinks afterwards. That would be nice. I have a very nice agenda for you today. Let me share my screen, and I have a few slides to share. It's coming. All right. There we go. So yeah, I already said this 36th meetup. There is one other thing going on in Leuven these days that you should be aware of. It's the AND Festival. It's typically a very big festival they have famous speakers, almost as famous as the ones here, but like Jimmy Walsh from Wikipedia. This is Nassim Taleb from Black Swan. You might recognize some other people here, like I forgot the first name, but Verstager from the European Union. This person in the bottom right, for those who don't know, is Mohamed Ridouani. He's the mayor of Leuven. So yeah, if you're interested in more, it's not data science focused, but more general innovation and what they call a forward-thinking conference. It actually started tonight. I didn't plan to have a Data Science Leuven meetup at the start of AND festival, but then AND changed a few times because they planned to do it physical, and now it's digital, and now it's hybrid or whatnot. Anyway, there's plenty to find out if you go to the AND festival. You can read more about it. I have two speakers for you tonight. The first one is Sven Cerneels from Aspen Tech. He's going to talk about transforming the process industries through AI and digitization. I just had a quick chat with Sven before we went live, and he has done a lot of different things in his career already. So definitely pay attention and feel free to ask him any question about data science. I'm pretty sure he can answer them all, but let's see, almost all. And next, we have someone all the way from Sweden. Is Simon Löfvender. I'm sorry if I mispronounce your name, but you can do a better job at that when you introduce yourself, from Solita. And he's going to talk about web applications in R and Shiny. And he also promised me that he would, because I'm a Python fanboy, for those of you who know me, I'm a Python fanboy. He also promised me that he would show how to do Shiny with Python, right? So that would be my ideal outcome of the evening, that I see how that works. Without further ado, I'm going to give the floor to Sven. So Sven, feel free to start sharing your screen, and then I'll project you.
Sure.
All right, here we go. Simon, I'm going to remove you and me from the stream now. Sven, the floor is yours.
Thank you, Chris. So thanks again for having me in Leuven Data Science Meetup. It's an honor to be able to present some of our views to you guys. So at first, I'd like to introduce myself. I'm Sven Cerneels, Senior Director Data Science at Aspen Technology. We are based in Bedford, Massachusetts. So our corporate headquarters. And so in what follows, I will actually give you a brief glance of what our core technologies are at Aspen Technology, how we think artificial intelligence or machine learning in the broader sense helps developing our core business verticals. I will give you a little bit of information under the hood, but not too much. Of course, no information that is not public or that would be considered confidential. And finally, I will also share, up to some extent, our vision, where we think industrial artificial intelligence is going. So to start at first, who is Aspen Tech? So Aspen Technology started as a university project from MIT. And so it was actually a government-funded project, which was started. And so the name Aspen actually has nothing to do with aspen trees, nor does it have anything to do with Aspen, Colorado. So it's actually an acronym. It means Advanced Systems for Process Engineering. And so Aspen started as a government-funded project to build simulators that would provide digital twins for manufacturing processes, particularly in the oil, gas, and chemical industries. And this is still our stronghold today, right? So we started after the university, the academic project. We founded the company in 1981, and so we started by productizing simulation software for chemical manufacturing processes, which is today still our market-leading product, Aspen Plus. And then gradually we digressed into the refining industries, where we acquired a company called Tech, and their leading simulation product, HYSYS, which is still also one of our market-leading products today in process simulation. And so these products are being used by process engineers, but also by designers of refineries and chemical operations. And these products are, so they have a very good reputation, they're market leading, and they are purely based on first principles. So you're, wherever you think of describing the physics, the chemistry exactly, using laws of nature, differential equations, then you're in the right space to know what is under the hood in Aspen Plus and HYSYS. Now, gradually, we became broader and broader, and the first step where Aspen Tech generalized was actually to jump into the world of process optimization. So not just simulating plants or designing chemical manufacturing plants, but also how to operate them and how to operate them optimally. So our product DMC3 is very well known in this space. But we also have manufacturing execution solutions. And so we gradually developed our software into becoming an all-encompassing solution for process optimization. Now, in more recent days, we have also jumped into the space of asset optimization. And this brings together the world of designing with operations, with maintenance and asset management. How do you manage the life cycle of assets in a manufacturing process? Now, since very recently, I can also say, so this picture has been extended just this year. So we also started vertical business units, and so we are growing outside the reign of oil, gas, and chemicals, and we just founded a pharmaceuticals business unit, which is our first vertical outside oil, gas, and chemicals. And so our products, they basically fall under three pillars. So at first there is engineering products, which are there to simulate manufacturing processes, and so they are being used in basic engineering, equipment engineering, typically also to debottleneck plants. Our manufacturing and supply chain products, which I didn't yet or only partially mention, are used also for planning and scheduling and for optimizing supply chain. So not just optimizing the operations, but also optimizing the entire value chain, the supply chain around these plants. And then finally, asset performance management is a business unit that exists for over 6 years now. And so there you could basically equate it with predictive maintenance. So we have predictive prescriptive analytics, root cause analysis, outliers, so basically anomaly detection, and then also trying to prevent anomalies, so that which leads into predictive maintenance. So these three pillars, they go together very well because it starts before a plant is being built or being expanded in the design phase. Then we have products to operate it, and eventually we also have products to maintain it. Now, what has changed in recent days? So this basically what I said up till now has been true for the last 30 years. And it up to some extent still is, but what is different? So now we are generating more and more data, right? And the process industries are a very good example of a vertical that generates a lot of data and that still has a very big potential to do more with the data that it actually generates. And so since we started generating more data, we built Industry 4.0 technologies, but we still have a long road ahead where we can get better and can get connected technologies, connected devices to have a novel way to interface with manufacturing operations. And so there is a big pressure to accelerate the integration of AI. And what we're seeing there is that even according to the World Economic Forum, so if you're a leader, you're generating much more in additional, so the percentual change in cash flow, you're generating much more cash if you adopt AI early compared to if you're one of the laggards and you're adopting it way later than the average in your industry. So, and this is why, because we are seeing this push, and we're seeing that AI is going to have a major impact also for our customers. So we want to help them be an early adopter of AI. And we think AI in the industrial sense. So what is industrial AI? That's where we think we can differentiate from the market in general. So we all know there is essentially not really a barrier for entry in this business. There is a broad candy store for data scientists out there in different classes of machine learning techniques, so whether you want to do supervised learning, regression classification tasks, or unsupervised learning, clustering pattern recognition tasks, sequential learning and optimization, so things like reinforcement learning, evolution strategies, NLP, speech recognition, or even cognitive computing. So for all of those, there are gorgeous public libraries. And I'm actually wearing a TensorFlow t-shirt today, which is one of the libraries that I'm citing here in the lower right corner of my slide. So there are wonderful public libraries for each of these components. And so essentially to just use them the way they are, there isn't really a barrier for entry for any company to start claiming its share of the market. Now, so where do we think we are different? So at first we observe that if you just look at the machine learning code, trying to embed machine learning in your products, it's only a small piece of the overall code, right? So there is a lot of code around that doesn't per se involve the core of machine learning. And so it's there where the knowledge of the manufacturing processes that we have comes in. So the domain expertise, knowing what we're doing, that's where we are strong as Aspen Tech, where we have these 40 years of experience. And so therefore, we think industrial AI will actually bring together, or has to bring together, data insights from these big data that are ever growing with the domain expertise that we have been good at for since the founding of the company and even before that. So we are in a unique position to actually bring these two worlds together. And so as a first step, we have started to productize hybrid models. And so hybrid models are models that are combining knowledge from first principles, from these pure first principle models, which are the ground truth for our simulation software, with pure machine learning models, which are the ones that you can, among others, you can also just grab off the shelf. So you can go to TensorFlow, Keras, grab your neural network and build a model off the shelf with minimal programming, actually. Or even a step beyond that, some cloud-based providers will do it for you. So there are pure machine learning models that need a lot of good data and will learn from the data, but not necessarily explaining why. And so they also only learn from those data they have. So they may not extrapolate very well, or they might actually also violate physical constraints. So if you're, for example, it's a very simple example, but describing a piece of equipment in manufacturing. So there is always product going in, there is product going out. The same with energy. You're investing an amount of energy that goes in or comes out, but there has to be a balance between the product entering the piece of equipment and the product leaving the piece of equipment. There shouldn't be any loss of mass. And so therefore, mass balance has to apply if you want to describe this piece of equipment in a realistic way. And so if you just build a machine learning model like an unconstrained neural network, plain vanilla TensorFlow, then actually it will not necessarily respect these balances. So we have to bring together these two worlds. We have to have some information from the first principles, some information from the machine learning models. There are, of course, various ways in which you can do this. And so presently, we think we have three ways of looking at hybrid models. So at first, there is the AI-driven hybrid model, as we call it, which brings together simulation data from our products and plant data from operations, and then builds a hybrid model. I will not yet go into detail how it does it. Secondly, there is a reduced order model where you only use simulation data and you try to approximate these simulations by machine learning. And then thirdly, there is a first principles driven model. And the first principles driven model will actually have the simulation as the main model. So the first principles, the physical equations are the main model, but machine learning is estimating add-ons to this model, such as unknown parameters in it, for example. So as an example for AI-driven hybrid models, so how does that work? So you have plant data, and then there is also simulation data. Now, the machine learning will take the plant data and will actually also process these data in a way that it actually makes use of some first principles. So there will be some laws of nature entered as the machine learning model is being built, which makes it an AI-driven hybrid model. And so that hybrid model will then be suitable to model complex processes for simulation where not everything in the simulation is known, and therefore the real life data are necessary to build a realistic model. But on the other hand, so it can also be used as an inferential sensor. So essentially predicting a property that is hard to model by first principles. So we have an example here from a synthesis reactor, which actually generates noisy and sparse data in different regions. But still, we would like some certain constraints to be met, and the model eventually must be interpretable. It's often a prerequisite in manufacturing that we know we are able to analyze how inputs impact the outcomes. And so our AI-driven hybrid models actually generated a very good fit here, showing the predictions for methane. And we also see that we are able to, compared to the original data, we are able to meet these first principles constraints. So we have a mass balance error that is negligible. Now, so I want to give you a little bit of a glimpse under the hood. So in terms of feature engineering, so feature engineering is a very elegant technique to implement nonlinearity. So of course, neural networks will estimate this intrinsically, but still using engineered features may help. And so some transformations to engineer features, there is an infinite dimensional space of functions that is possible. Of course, we can't screen all of them. And so in this function, just to give a couple of examples, we could use parabolas, we could use these first principles, these laws of nature to do some feature engineering. We could also use splines, which generalized additive models are doing, or any other type of function actually. And so then, yeah, the question becomes, which ones do you pick if you don't want to overfit? And also, which ones do you want if you still want to have interpretability? So for example, if you select all three of these transformations that I'm listing, if log x1 has a good effect, but x3 over x1 has a bad effect, how do I interpret that in practice, right? So this is actually not better than a black box model because it's still very hard to get my head around how this thing is working in practice. So one thing that we have implemented is an approach based on reluctant modeling, which is a new technique to select variables, originally proposed. So it generated from the Tibshirani academic family, as I would say. So it was first proposed by his son, Ryan Tibshirani, and then his father, Rob Tibshirani, jumped on the boat and also wrote a paper on reluctant models. And so this is an approach where you at first fit a model with only linear variables, and then afterward you fit the residuals of this linear model with a model with a set of transformations, and then you use variable selection to select which transformations am I going to apply. And this so this model is by definition reluctant to retain anything that's nonlinear, and to retain so it will retain as few as possible of these nonlinear transformations. And so if you compare a generalized additive model, which would fit a spline variable around each variable as shown here, then a reluctant generalized additive model will likely not fit a nonlinear function for these first two ones that look approximately linear. In a GAM, they are not. In a reluctant GAM, you will get an exactly linear transformation here, which is the same as no transformation. But you will still retain the splines for those variables where it really matters. So this is it's something where we have filed some intellectual property, and so I will not jump into that, but it's one piece of models that we have under the hood. Now, jumping to these reduced order models, the reduced order hybrid AI models, they have a different nature. So they don't use any operational data. They just start from simulations. And they're a type of model that you would want to use if you have a very exact simulation based on a lot of differential equations, which solves very slowly. And so there's many of those actually in operations, in refineries, in things like naphtha crackers. And so these models are very accurate. They're often built on based on hundreds of thousands of equations. It's not unusual to have a model that contains 150,000 equations. But therefore, because it has to solve all of those simultaneously, it becomes very slow. And so you can't really do that in real time. Therefore, building a reduced order model builds an attractive alternative. So if you have the time to run many simulation scenarios offline and get the corresponding responses for it, then you can actually use those to train a machine learning model. And then afterward, the machine learning model can substitute the first principles model in real life. Because as we all know, a machine learning model prediction is instantaneous. So it comes down to training it based on these simulation data. And so therefore, we also have developed very good examples. So as an example, I'm showing here a reduced order nonlinear fluid catalytic cracking model. And so this can be used for planning optimization then in conjunction with our supply chain optimization software. And so as you can see, the actual predicted, so I'm plotting parity plots, predicted versus actual for some mass flows associated with this piece of equipment. And so the predictions are all, they will never be perfect, but they're definitely passing the test of quality that we had preset. And what is above all notable is that if we use the purely first principles based model in our simulation software, it runs 15 times slower than the reduced order model. So this reduced order model can be used in real time for planning purposes, whereas the first principles model would take forever to calculate, right? So finally, the first principles driven AI models are AI models where the first principles, the simulation is still in charge. So there you're talking about a simulation that is representing a piece of equipment, so a phenomenon like a continuous stirred tank reactor here. And so for this phenomenon, you have a first principles driven model, but you don't have all information needed to fit it accurately. this happens often in practice. For example, describing reaction kinetics, we all know Arrhenius's equation. We know there are rate constants in those equations. The rate constants can be derived from chemical experimentation, but there isn't always time or resources for that. And therefore, so often these parameters are unknown, or they have to be derived in a very quick and dirty way from process data. And what we are offering now is a much more convenient way for the engineer to go about that. So the engineer can have their simulation model that represents the piece of equipment with the unknown parameters in it. So then we have a neural network behind the scenes that the chemical engineer doesn't even have to interact with. And so we provide the option for the engineer to enter operational data into the simulation. And then what will happen is the neural network will learn from the data what the optimal parameters are in the first principle simulation. And so the first principle simulation will act as the final layer of the neural network, and therefore the neural network's weights will be optimized so as to deliver the optimal parameters in the simulation. And so the engineer doesn't have to do anything there. So they just feed in the data, click a button, and you will get a first principles model with optimal embedded parameters. And a good example of that is a simple separator model, so a membrane model. Membrane separators are widespread, particularly in natural gas treatment, but not only there. And so in these membrane separators, split fractions are parameters that have to be set. So we built a first principles driven model that estimates these split fractions automatically. And as you can see from our parity plot again, so the predictions are matching reality very well. So this is an example where you would still want to use the simulation software as the dominant piece of software, but you have embedded AI or machine learning in this case is a better word, but you have embedded machine learning in the first principle simulation software that greatly enhances the user experience. So finally, these hybrid models, we have an ecosystem of product, right? So how do you deploy them? How do you work with them? So we have three options. So either you deploy them in the apps. So if you use our simulation products or our supply chain optimization products, you can deploy these hybrid models as an object there. You can also deploy them online, put them in real time and observe what they are predicting in something like a DS, so a digital control system, which can be seen in operations in real time. But you could also plot the predictions, of course, as we are going to learn from Simon. In 15 minutes, you could build in our Shiny dashboard and plot them there. Or finally, you could also deploy them on the edge, which can often be very beneficial, because if you have many pieces of equipment that are geographically dispersed, which happens in many situations, but for example, like in a field of windmills in the North Sea, I know there is a big wind farm in the North Sea where these windmills, they're offshore, they're difficult to reach. So if you want a model to make predictions in real time at the piece of equipment, if that has a value for you, then these models can be deployed on the edge as well. So now, finally, I want to share a little bit our vision of where do we think this is going. And so we think our vision encompassing where industrial AI is leading us is the self-optimizing plant. So we see a plant that actually is self-optimizing, is delivering value in many different ways. So it will yield safer operations, because if the plant self-optimizes, incidents will be detected before they happen, and therefore it's automatically safer. This both holds for incidents involving physical persons, operators in the plant, as well as involving environmental events. So you will have safer operation, reduced emissions, but also, of course, no incidents is less downtime, which means improved reliability, and eventually also we will have higher margins because we're able to optimize in real time. And our motto is plants will operate safer, greener, longer, and faster. So I think we are definitely a company committed to ESG, environment sustainability, and is helping to run more sustainably by delivering the self-optimizing plant. So a couple of characteristics that we think a self-optimizing plant should have is it should be self-learning. So there should be an option where an automated data stream is coming in, and then machine learning models have been set up in a way that they automatically look at this data and learn from new data. Then they will detect if the data are not deviating from what it has seen before. That adaptation is necessary, and then the models will be self-adapting. And finally, these models should also be self-sustaining. So they should work together to predict the future state, and thereby, if the future state is predicted well, it should sustain itself. So this was a tiny little piece of information I would like to share about our future vision, and thereby I would like to wrap up the presentation. So thank you so much for having me in the Leuven Data Science Meetup.
I'm muted. Classic. Thanks, Sven. Thanks for this introduction into well the kind of models that you guys built at Aspen Tech. While we wait for questions to come in, I do have a question for you. So you talked about two kinds of models, like first principles models or like models based on, like, I don't know what you call them, machine learning models, basically who have no idea what they're looking at. They could be looking at potatoes or customers or the sky. It's the same algorithm that runs, right? And then you say like, okay, the best is a hybrid approach, and you show a bit like how those could work together. But would you say that, let's say we fast forward another 5 years, technology has evolved, like TensorFlow, whatever, 8.0 is released. We have even more computing power than we have today, like exponentially more. Would you expect that by then, like the expert models or the first principle models will lose importance and like there's nothing that your TensorFlow algorithm can't solve? Or will you think there's always place for the two models in a solution?
I think there will always be a need for first principles. And the reason why I'm saying that is that I think while looking at your scenario, if computing power is increasing and so the models are more and more powerful and are able to learn dependencies by themselves, I think that, you never have data describing the world. And the issue with pure machine learning models is that they have a very hard time extrapolating beyond the training data they've seen. And the more high dimensional you go, actually, the more data you will need to successfully train models. And on top of that, I think so. You already see this manifested. So there is also the additional need that we need models that are respecting all types of different constraints mandated by laws of nature or by the pieces of equipment they are representing. There is also the demand for interpretability, where, of course, you can go into the debates like Jan LeCun versus Gary Marcus. The one thinks everything has to be interpretable. The other thinks it's, as long as the model is good enough, you don't need to interpret anything. So personally, I tend to be more on the side of people who think you need to be able to interpret what is going on, because here we are looking at real world operations, right? So if you have a pure black box model and it is steering a plant in a certain way, and then all of a sudden there is an environmental incident, there is a leak into the river, and then we need to investigate why that happened, right? So the explanation the black box predicted it is not satisfactory in that context. And so there is a growing body of legislation that is actually forcing companies to have interpretable machine learning models, also in finance. So according to IFRS 9, predicting credit risk for customers, You can't just have a black box model. You have to have a model that is up to a certain degree explainable. There's many other corners as well. And these first principles, they can offer you this level of explainability that you're looking for. So for various reasons, I think there will be a growing interplay between machine learning models and first principles, but I don't think the machine learning models will per se totally outlive the first principles models. Even though you could philosophically, you could think like if the machine learning is powerful enough, then yeah, you could bring it to the point where it learns the first principles. So it basically learns the shape of these differential equations and then starts solving them for you. But I think you should we're still at the point where you should tell them that is what it has to learn. And that's then the level where you're bringing in domain expertise.
Yeah. No, I think it makes a lot of sense what you say in my limited experience for these kind of cases, because, well, I do see like these expert systems or these first principles models, let's say sometimes an expert also overemphasizes his own knowledge about a system, and he puts like things in there that don't make a lot of sense, and it's relatively easy for a machine learning model to outperform like a first principles model. But then again, I can imagine in more advanced use cases that you probably see day to day, it's not true, and you actually have very good first principles models. I still need to see them. All right. We have a question from Istvan, and he asks, can you give a practical example of how you applied reluctant modeling in practice without revealing IP? And then he has another thing, an example where it shines compared to more traditional methods.
So yes, so the way it essentially works is in line with what I presented in the slide. So what you're doing is you're having an infinite dimensional space of functions that are representing the potential feature transformations possible. And so what you do is you identify a subspace of those where, again, you use your domain knowledge, right? So the domain knowledge is going to determine which is the relevant subspace to look for. So for example, in an engineering space, I'm citing a professor who we have a good relationship with, Professor Venkata Subramania. So he often says, like, in the space of possible transformations, an exponential of an exponential doesn't make any sense at all, because there is not a single law of physics which is relevant to engineering where you have e to the x being in any way relevant. So because of that, that function should not be a part of the bucket that you start screening for. And so you use your domain knowledge to build a set of functions that are likely going to represent operations in real life well. And then reluctant models will help you to select the subspace of these functions that are relevant, that are really contributing to predictive performance. And so this, which ones it are, it really depends on the piece of equipment. So I also mentioned that we did file IP on this, where the IP isn't about reluctant models because that's public knowledge, but the IP is about which specific transformations might apply that are very relevant in an engineering context.
All right, cool. Then we have another question from Rafael de Oliveira. He says, great presentation. How much do you think human resources, completely different topic, how much do you think human resources need to change for implementation of this tech? Do you think enough offering explanations to experts that does not know the technology behind? I'm not sure how to parse this question, but I guess, like, can we do this? Do you think we can apply this to human resource management?
Yeah, totally different topic. It's not really it's not really the domain knowledge, or it's definitely not related to something that we as a company are selling. But I can have an opinion about it. So I think you could build machine learning models that are learning skills of people and are reading resumes. So to a large extent, that's definitely already being done by companies like LinkedIn, owned by Microsoft, and many others, Glassdoor. So you build machine learning models that are trying to associate read resumes and then associate skills with the desired outcomes in the company. And I think the next level there is likely to actually also link it to the deliverables of projects that future employees might be working at. But as a remark there, I definitely also like to heed that these approaches, there is a significant potential for having biased predictions, and so the type of bias that you wouldn't want, which is biases against certain groups in the population, which might be inherently there because it's your training data. So I think that there is this type of machine learning applications. They have to be developed with a lot of care to assure that there is fairness in the outcomes.
Yeah, and there are cases where it wasn't the case, right? I heard of a story where they filtered out, for instance, gender. So there was no gender information in the machine learning model. But then in the description, so like description about male applicants would be about he did this and he blah. And then for females, she did this and she did that. Yeah. And actually that was a predictor for the salary they would get or something, or the performance they would be rated. So it's terrible. But indeed, if it's present in the training data, if you're biased company, then your machine learning algorithm would also be biased, right? So yeah, okay. But thanks for the explanation. Also, thanks again, Sven, for the talk. It was very entertaining. It was very interesting to see that field because I don't see it a lot in practice, so I learned a lot today. With that, I'm going to bring Simon to the stream. Sven, I'm going to remove you from the stream. Thanks again for your presentation.
Yeah, thank you again.
All right, bye. Simon, hi. Welcome.
Hello.
So you're going to do the second presentation of today talking about R Shiny. So I'll add your, there you go. And I'll remove myself from the stream and then the floor is yours. You can go.
Thank you very much. As you revealed, my name is Simon, and I work as a data science consultant at Solida, which is a consulting firm who offers services in anything from cloud and data to strategy, essentially. And we have offices around Europe in Belgium and Leuven. I hope I pronounced that correctly, Germany, and the Nordics. And I myself, I'm based in Sweden and Stockholm. And I've been a consultant for a few years now. And before that, I worked at a company in digital advertising for another few years. And my field of study and background is in statistics. And today I'm going to talk about and share some thoughts on R Shiny, which is a R package designed to build web applications straight in R, meaning it's essentially a framework to deploy your data science solutions such as reports, models, visualizations, or dashboards. And I'm going to talk a bit about how this works and also some of the benefits that I see organizations can achieve by implementing and spreading solutions using this type of framework. And myself, I first encountered Shiny a couple of years ago in a previous role where I started building many web applications to give the organization access to some standardized models and analysis on a wider level. And this essentially meant that we outsourced the running of standardized solutions to the end users themselves instead of having them to go through me or another analyst for repeatable tasks. And yeah, this then had the benefits of analysts being able to focus on new tasks while getting more data science practitioners in the organization, who then also got a better understanding of the subject over time. And this is a quite brief presentation, but I'm gonna go through these following parts. First, a bit, what is Shiny and why I think it should be used. And then a bit about how it works, some thoughts on hosting and deployment of the actual application. And then I prepared a short demo application where, as Chris revealed, we'll look into how you can combine Python and R in a Shiny application. So as mentioned, first and foremost, Shiny is an R package designed to build these web applications, which means that it is an add-on to R. Though I think it has almost grown out of that definition in the last few years to become a production-ready framework in its own right, really. So what Shiny allows us to do is to build these applications straight in R, and given the possible output and the possible complexity of the apps, we can do that with actually relatively low effort. So it is quite simple to build this visually good looking applications backed by the entire ecosystem of Python and R without knowing HTML, CSS, or Java, since Shiny takes your R code and then translates it automatically to the relevant formats for a web browser to be able to render the application. And this means that the possibilities on what we can build are essentially endless, and it can be anything from deploying a model to building dashboards, reports, or building solutions for model monitoring. So in short, it's a very flexible way, and any task you can do in R, you can essentially repeat in Shiny and spread it to others that way. And even if you don't need to know CSS or Java, for instance, you can integrate those languages with your Shiny code to create these custom web applications, which essentially looks like professional websites. And Shiny was built already in 2012 with the purpose of prototyping simple models with a few reactive components without any thought on that it could be used as an end product, really. It did not take too long before people realized the potential in this, though, and started building it out more and adding features over the year until today has become this production-ready framework maintained by RStudio. And today it also has this quite large and active community, and Shiny developer is an actual job title as well. So you can see listings for Shiny developers if you search for it. So why should you use it then? So it's a very flexible and powerful way to standardize anything analytics or data science and make it available to others. And we're not just limited to visualizing data. We can create this complex application that wrangle, manipulate, and do some operation, apply some model on the data as well. And we do have access to essentially all of Python and R together with these powerful visualization libraries, ggplot, for example, all in one single framework. And especially the Python support has become better in recent times by the reticulate package in R, which allows us to mix R and Python in the same scripts. And since we can get these and create these applications without prior knowledge of web development, what we get for the hours we put in when we build something in Shiny makes it relatively low effort. That said, though, it's not easy in that sense. You still have to code and you have to know R. So if the goal is to only maybe visualize data using standard formats, no code tools like Tableau or Power BI may be a better solution in those cases. But since you can make your applications quite easily available, I think it's a great tool to spread data science throughout an organization and concretize it for the end users. Then I'd say that connectivity is another big selling point, since these applications can be connected to essentially any data source which we can connect to in R and Python. And then finally, we have that hosting is made easy by RStudio's own solutions, but we can also host it basically anywhere by Dockerizing the web application as a maybe more flexible solution. And since it is an open source framework, it can be a quite budget-friendly way to deploy your data science solutions. And Shiny is still sometimes compared to these pure BI and visualization tools like Tableau or Power BI, which I'd say is quite unfair, really, since Shiny is so much more than that. So if we're looking for a visualization tool only, it could be a relevant comparison to do. But if we want your solution to do anything more than just visualizing already available data, we have to compare Shiny to the additional tools required for completing the same task as with these BI tools. And as of now, these BI tools offer quite limited functionality in addition to visualization, such as data wrangling or putting your models in production, which means that we first then have to deploy our model using other tools. And then maybe we have to write the results a table in a database and then plug in your dashboard tool to that table. So what Shiny does is that you circumvent this step and you have everything in one solution instead. That said, though, I think that, for example, Tableau, they're working on their R integration. So it might be a competitor to Shiny when they grow out this functionality, which I think they will do in the quite near future. And then another benefit that I see from using Shiny is when we use it as this tool to distribute data science within an organization. And by distributing, I mean to outsource standardized analysis to end users from the data scientist or the an analyst by building this application performing standardized tasks. And these tasks doesn't have to be completely repeatable, since Shiny allows for some reactive components as well, so we can tweak the solution depending on the situation as well. And this is, of course, not true for all organizations, but from what I've seen in various roles is that data science teams are usually quite isolated from the rest of the organization, and this results in that what they do and what we do seems almost abstract to the outsiders and the ones who maybe actually use the outputs from the data science teams. And this results in that we have these information gaps between data science teams and the end users who on average usually sits on more domain knowledge. So this results in that we get end users who does not maybe understand how the outputs are obtained, and from their perspective it could look like this black box. So they consequently have a higher barrier to ask these additional questions to develop solutions further. And we also get these data science teams who maybe do not have a full understanding of how results are used, and this may result in that they build suboptimal solutions. And there are, of course, more ways than Shiny to bridge this gap and work on increased collaboration between teams, and it may not be suitable for all organizations. But in some cases, I think it can work as this node where these business functions meet. And this would then result in that we get end users who obtain a higher understanding on the workings of the models and the result they use. And hopefully we will have such users then organically to start asking more questions, such as, can we also do this? Or it would be better if we have the information presented in this way instead, or we would like to add this piece here because that would really help us. And starting to ask those questions, I think, is key to make solutions more optimal with respect to how they are actually used over time. And I think that this also has the benefit to data scientists, who will then learn how to also ask better questions as they get a better understanding of how the results are actually used. So to summarize these thoughts a bit, if we make these applications available and transparent and outsource this standardized analysis to the end users, we would naturally have it that data science become less abstract to other business functions. We get more data science practitioners and a better understanding and integration between the data science and the other teams. So hopefully what we'll move to is this positive feedback loop I'm trying to visualize in this picture here. So I think that this has the benefit of increased collaboration, understanding, and then more organically will allow the organization to ask better business questions, which of course in the long term will increase business value. So this is just one example, of course, of how Shiny can be utilized with a specific purpose of reducing workload for analysts and standardizing these repeatable tasks to spread data science. And this may, as I mentioned, be not how every organization should utilize a tool like Shiny. And in some cases, it can be used as an internal tool for data science teams, for example, used for model monitoring. I think it's a great potential application to build explainable AI solutions, or to just put your models out in production in general. So that was a bit on why I think Shiny should be used. So now moving over a bit to how it works instead. So on a high level, Shiny takes our code, translates it to HTML, CSS, or Java, which then this browser can read and render to a visually appealing web application. And this is made possible by a framework called Bootstrap, which you may have heard of before, as it is one of the most popular front-end frameworks out there today. And it was created by Twitter and was open sourced already back in 2011. And it was built so that developers didn't have to reinvent the wheel every time they wanted to design a web page. So at Twitter, it was used to build this web application and was spread internally before it was made open source and leveraged to create Shiny with the purpose of first then being able to quickly create applications to prototype models. So a Shiny application is, in its simplest form, made from two key components in the form of two separate R scripts called UI.R and server.R. And UI, as you may guess, stands for user interface, and it is where we define what the application should look like. So we describe which features the app should have, such as the graph objects, the buttons, reactive sliders, tables, etc. So we simply define the design of the application. And the code here is not traditional R code, but follows Shiny's own syntax. And in server.R, all the heavy lifting is performed, and it can be described as the back end of the application. So here we place the code that is executed upon a button press or another reactive component in UI. We create the graph object we have defined that should exist in UI.R. We connect to a database, we import the models, we wrangle the data, and so forth. And the code here is a mix of pure R or Python code and Shiny's own syntax. And Shiny is based on a reactive programming model, similar to a spreadsheet, really. So in a spreadsheet, you have a formula attached to a specific cell. So when a value in a cell changes, the output changes according to this formula as well. So it's the same really with a Shiny application. The formula stays the same. So the chart object or the table, which we have defined in UI.R, they are the same, but the values in them change depending on the input. So in this picture here, we see a bit more detail on how these two scripts, server.R and UI.R, work together. So an input widget we have defined in UI.R, it could be a reactive slider, it could be a graph object, or a table that we want to populate with the information. Then we have it that we, in server.R, we match this widget parameter with a specific information, and then we send the render object back to UI.R, which will then send it back and show the finished object. And this is how it can look like in its simplest form. So we have a very, very simple example of an application. So in that example, we just use UI.R and server.R. But if we want to make more complex applications, we have to consider more components. And it could be a global script that contains functions that the app should always have available, or it could be libraries that we want to be accessible at all times. And it could also be R or Python scripts that are triggered to run in specific parts of the application, which could be a good idea really if we have a very complex app that makes sense to modularize. So certain operations are only triggered in subsets of the application. And if the application is expected to grow over time, it can make sense to actually modularize it, where we have scripts for each module separately to manage the application easier. And this is something I wish I started doing for one of the larger applications I built some time ago, which I, of course, didn't. So the server script grew to some tens of thousands of lines of code, making it challenging to maintain, to say the least. And then how to best deploy your application is quite case specific, and it depends on who the users are, the amount of users, what data and connections you're going to use, and the quantities of it as well. Also, the processing power matters. How much do you need? And the simplest way to deploy your application is through Shiny Apps, which is RStudio's own solution. And they have several plans depending on your needs. And if your organization uses RStudio Connect, they also offer a seamless integration with these Shiny applications. And there are then a number of other solutions, and one of which is to just Dockerize your application and essentially host it anywhere where Docker can run. And then we have something called Shiny Proxy, which is an open source alternative to more enterprise hosting, and they offer security and scalability for free instead. And Shiny Proxy also relies on Docker, but they offer a bit more components after Dockerizing the application. And this could be a good idea if you have many users who expect to use the application at the same time, since one new container is then started for each unique user, making it quite scalable. And then I thought I was going to show a bit of how it can look like. So I prepared a quite short demo application. So in this little module here, we have an application that is connected to Twitter. It fetches some tweets, does some sentiment analysis, just some descriptive statistics. Then we have that we perform something that maybe you can't do with other BI tools, such as the topic modeling here, where we extract a topic for news tweets. So we have it what they're talking about, and also can look at the engagement and sentiment by topic and so forth. The point here isn't really what it does, since this has limited usability, but essentially how easy it is here to integrate your application with Python code and combine R and Python. So here we have first connected to a Twitter API, collected some data, and we just create a text vector from that, which we define here, and we call it sentences. And then through the reticulate package, we can just write Python code here in the same script. So we import a fine-tuned BERT model from transformers, and then we can call our R object, which is called sentences, by just putting this here and then apply the model here. So then we run this part here in Python instead. And then we want to get the object back to R again. We just say, all right, so we want to access this object from the Python part up here. So it's really quick and easy to integrate these two languages these days. So the Python versus R debate is maybe we don't have to pick sites after all. We can just use both. And then going back to the app, we also have another part here where we look at some explainable AI or interpretable machine learning, where we just have a quite simple model really with some Lime explanations where we can just choose the employee. So this is a sample data set where we have employee attrition. So we can look at the probability that the employee is going to leave, and then we have the top factors here. So this, I think, is a great use case for building an application, which may look a bit better than the quick thing I put together here. So that's something that's a great usability using Shiny. And then we also have something which we potentially, I talked a bit about how we could outsource standardized analysis to end users. And this could be an example of that, where we have a time series and we have a module fitting a time series model to this data. And you have a few choices here when you can tell the model what to look for. So this under the hood here, we have a Bayesian structural time series model. So we tell it what seasonal features we can expect to see here, and then it fits the data. We do the training, we test the model, and we see how it performs on the data, and then we can use it to forecast and maybe export the results later. And this is something you can teach people to do, so it doesn't necessarily have to go through an analyst to do these tasks anymore, and you would have more people being able to do this by just standardizing parts of it in a Shiny application instead. So I'm not sure how we are on time, but I think that's about what I wanted to say today.
All right. Well, cool, Simon. Thanks for sharing, and also thanks for the demo. I was thinking, like, you're talking about Shiny so much now. Show me, and then in the end, you get like, and here's the demo. So I liked it a lot. Thanks for doing that. Let's wait a bit until there are questions in the comments. Let's see. No, there's nothing yet, but we have some delay. So I'll do the first question. You already said about there are some deployment options, like just wrap it in a Docker container or use Shiny apps, or use that Shiny proxy thing. I don't know if you have experience with this, but you also showed, like, if you have some more advanced Shiny apps with a database connection and with some like complex models and a lot of data and stuff. In your experience, would you always go for this Shiny apps approach, or do you by default wrap everything in a Docker container, or what is your default approach to this?
Well, my default, I would say, is the Docker container, and then you do the database connection in there as well.
Yeah. But then, I'm sorry if I ask a stupid question, right? But then if you just wrap it in a Docker container and put it on EC2 or something, then there is no security or credentials or login or any of that, right? You just point it to a link somewhere and you share the link with the rest of the organization. Or how does that work?
Yeah, in that sense, but you would need to wrap some security on it as well. And I mean, there are some more simple versions which you can actually put in your application as well. But maybe you would have someone who is a bit more knowledgeable than me to actually put that up. I can build the application, but I can't really do the enterprise security, so to speak.
All right, but that is fair. It's just interested, but thanks a lot. There is a question from Istvan again. He says, hey, we use R Shiny a lot in production. Sometimes a slick design is important for some clients. Do you have advice or tips in that area? Third-party libraries, maybe?
Yes, there are a lot of, or not a lot, but I think there are a couple of slick design options. I'm not sure if you used something called Argon Dash, but for example, this demo I showed here, it's built on that framework, and that also allows you quite easily to mix your predefined shell in that case with some custom CSS. So you just put that code as well, the design code in, for example, the UI.R, or you have it as an external script, and you could have someone who is maybe a bit more to the design part to actually customize it a bit.
Yeah, that's cool. Indeed, your dashboard looked very sleek versus some other RShiny dashboards that I've seen. So it's, what is the plugin you used, or the extension?
It's called Argon Dash.
Argon Dash. All right, cool. Then there's another question from Vladimir, who says, hey, do you have an opinion on Dash versus Shiny?
Well, I wish I did, but I haven't really tried out Dash, but I think it's very, very promising as well. So, I mean, I don't really know if you put them both against each other. Maybe it goes down to your preference at the moment. I started looking a bit at Dash a couple of years ago, but then the functionality wasn't really built out, so I'm not honestly sure where it is today. So a couple of years ago, I would have picked Shiny, but I don't really know.
Okay.
Today, actually.
Okay, cool. That's fair. All right. I see there are no further questions. So then I'd like to switch to questions for the audience, actually. So I'm going to send a link on YouTube, and you should all go to that link. So I'm going to ask you a few questions about data science in general. I see one more before I switch to my link. Dimitri asks, is it difficult to convince Tableau Power BI users of the Shiny alternative?
In my experience, it can be quite tricky, actually, and you usually have to really sell the benefit of using this code library instead of using something that is quite easy, and you have the plugin click and play in Tableau when you already have it connected to a data source. But as soon as you want to do something that is not just visualizing data, I would say the benefit is huge from using Shiny. So maybe you would have to sell in that, all right, but we're not just limited to just visualizing data now. We can also offer this model here in the same framework.
No, that makes a lot of sense, by the way. I think if it's just pure visualizations, then it's hard to convince these users to start using something else. But indeed, it's about doing more than what you can do with Power BI and Tableau, right? So if you position it like that, I think it makes sense. All right, Simon, with that, I'd like to thank you for the presentation. I liked it a lot. I learned a lot. I also saw that you can do Python now with Shiny, so I should definitely try it out. Thanks a lot for joining.
Thank you.
All right, and then so for the other ones, I promised I would post a link. I posted a link on YouTube. So what I want to do is a quick Mentimeter to check, and I'll share my screen in the same time. I want to quickly share my screen to check what your guys' expectations are about Data Science Leuven, if you will. So if all is well, you should see a link posted on the comment section of YouTube. So if you go to that link, or if you just go to what it says here above, you go to menti.com and you use the code 50688267. I have a few questions for you. And the first one is, why do you join Data Science Leuven events? Is it you're just interested in data science in general, you want to learn more about it? Is it because you want to see concrete use cases at other organizations? Is it, well, it's shifting around, but is it the mathematics things, the mathematics side that you're most interested in, the business aspects, or the engineering aspects? I see two answers have come in, 3 answers already, so I'll wait for a bit until this is updated with a bit more answers. This will help us, by the way, to shape future talks and events. Oh, my engineering heart breaks if I see the engineering aspects are on number 5. So none of you are interested by the engineering aspect, but that's okay, I can handle it. Most of you, what is it? What is the trend we see? It's data science in general, use cases at other organizations, those two are at the top. Mathematics as well, yeah, those 3 switch around a bit. And then only business aspect and engineering, those are the 2, I would say, less interesting topics to you. Okay. By the way, I am going to get feedback from Istvan right after this, because he's going to say that I did my survey wrong and I should ask the questions differently and everything. But anyway, it's just a way for me to get some insights. Okay. I think mathematics has won, or 19 people who responded. So mathematics first, then use cases, then data science in general, then business, and only 5th engineering. All right, fair enough. Thanks for that. So next question I have is rate the following statements. So I see some of you already did. So in general, do you like the talks delivered at the meetups? Do you learn something new whenever you join? So you can either strongly disagree or strongly agree or something in the middle. Do you think we should keep on doing these live streamed events even after Corona? So I hope we one day go back to normal. If we can have like the live events in the auditorium again. But on the other hand, now it's cool that we can invite speakers like Simon all the way from Sweden. He's like a mouse click away and he joins our meetup. So that is not possible, right? If we only do physical events. So I'm curious to see what your preferences are here in terms of I see it's a bit mixed, both the drinks at Stuck and the live stream. So some of you are really fan of the live stream, I can see. Of course, I'm asking in the live stream, right? So Istvan will probably say, well, you should ask the question in the physical meeting as well once we have them again. So this might be a bit biased, but anyway. So yeah, some of you definitely want to keep on doing the live stream. Some of you are definitely missing Stuck. Some of you don't care about the drinks at Stuck either. Okay, fair. Maybe you're a bit further away. I like this, right? I like that you enjoy the talks and you learn something new, because that's in the end, that's the purpose of why we're doing this. So that's cool. Also, big thanks to our speakers, of course, who make this happen. And then these results are a bit mixed. I think some of you want to keep this live stream. Some of you just want to go back to physical meetups. So let's see if we can combine this. And then I have one final thingy, and it's more open-ended. So how can we improve Data Science Leuven meetups? It's if all is well, you should be able to type something here. Would we do more talks, less talks, longer talks, shorter talks, different topics? Maybe talks with more demos, maybe more hands-on sessions, maybe more discussions, hackathons. Well, whatever pops in your mind. How can we improve Data Science Leuven in the future? All feedback is welcome. I'll wait a bit until the answers appear, because there is some time delay between me saying this and YouTube broadcasting this. But apparently nothing is coming in, so I guess Data Science Leuven is already perfect. It's nothing to add, nothing to subtract. I'm gonna wait for a bit more, but then I'm gonna stop staring at the blank screen. All right. Drinks, shorter but more talks per session. Doe zo voort. Now it's all of a sudden coming in. Wait, how do I go? Anyway, better questionnaires. I'm sure that's Istvan. Hi, Istvan. Keep it online or hybrid. Some talks could use interactivity, more real-life use cases. Keep the spirit alive. Yeah, that's an important one. I'm serious. I keep the spirit alive because I think some people, let's say some people in my direct contact group are a bit down because of Corona. I think we all feel a bit down. Everybody's fed up with staying at home all the time. So that's also exactly why we wanted to keep on doing Data Science Leuven, that at least you have that monthly thingy coming back. It's not as fun on YouTube as it is in real life, but anyway, we try to keep consistency. Yeah, keep it online or hybrid. I like that a lot. There is a way to do video recording at Stuck, but honestly, I have no clue how that works. So we need to figure out if that's a real possibility. More real life use case is also a nice one. The problem with that is often if you talk to companies, they often want to share about what they're doing high level, but they don't want to go into the details because they consider that to be very private. They can't share. It's the same. I mean, it's the same where I work, right? We can't share everything we do in our day-to-day work because it's all confidential. But we'll try to focus on that. Try to focus on more use cases. Interactivity in talks that could also help. I like this Mentimeter thing where you ask questions every now and then. I also use it whenever I have to give a talk for my company, and there's a large audience. I always ask like, hey, fill out this Mentimeter to get a bit a sense of the audience. All right, let's stop sharing this thingy. With that being said, I think let's turn off this banner. Boom. I think we can wrap up. It's 10 to 9, so even though we missed one speaker, we still got a full event, quote unquote. So thanks all for being there for our 36th meetup. The next meetup will be in May. I don't know exactly which one, which day in May, but I'm looking forward to seeing all of you there. Thank you all, and see you next time. Bye.